welcome back. In this video, we're going to talk about the law of natural growth or decay, and we're going to start with an example. Let's start with this problem from a recent worksheet. Problem number 2 says a bacteria culture starts with 500 cells and doubles in size every hour. Part A says find a function that represents the size of the culture at time t. Part B says find the rate of growth of the culture after 6 hours. So in part A, we're going to come up with a function of t, function of time, so that we can predict the population t hours later, after time 0. So let's first give our function a name. Let's call it p for population, p of t, because it's a function of time. And let's write down the first few values, the population for the first 3 hours. So at time 0, the population is the initial population, 500 cells. So we can write down p of 0 is 500. An hour later, so p of 1, the population has doubled. So we're just going to multiply the initial population by 2. So p of 1 is 500 times 2. And then p of 2 is going to be the previous population, 500 times 2, times 2, because we're doubling again. And then after 3 hours, p of 3 is going to be the previous population, 500 times 2 times 2, doubled. So we're multiplying by 2 again. And notice we do have a pattern. So p of 0 can be written as 500 times 2 to the 0. P of 1 can be written as 500 times 2 to the 1. P of 2, we can write that as 500 times 2 to the 2. And finally, p of 3 is just 500 times 2 to the, you guessed it, 3. So now we can write down p of t. At any time t, the population is going to be 500 times 2 raised to the power t. All right. So now let's find the rate of growth after 6 hours. So first let's just find a function for the growth, for the rate of growth, by differentiating. So dp dt, the derivative of the function p with respect to time, is going to be 500 times the derivative of 2 to the t, and the derivative of 2 to the t is just 2 to the t times natural log of 2. All right, so after 6 hours, we just have to compute dp dt evaluated at t equals 6. So just plug in 6, and we get 500 times 2 to the 6 times natural log of 2. And now because this is a word problem, and we're talking about cells, and we can't have a fraction of a cell or a 2/10 of a cell or whatever. We got to get a whole number. So we're going to put it in the calculator and round to the nearest whole number, and we get 22,181 cells per hour. All right. So now, just for a minute, take a look at that derivative, dp dt. Notice that dp dt is really the function p of t times a number, the natural log of 2. So the function, the population function that we got, satisfies this equation. The derivative dp dt is equal to some number times the function p. And what that equation says is that the derivative, or the rate of change of the function, is proportional to the function itself. That's what it means when y is equal to constant times x. That means that y and x are proportional. So here we have the derivative is proportional to the function. Well, any function that satisfies that or has that property is said to obey the law of natural growth or decay. So a function that obeys the law of natural growth or decay must have this property where the derivative of the function at time t is proportional to the function itself. So the derivative, dy dt, is equal to k times y for some constant k. And this equation, remember, is a type of differential equation. Remember, a differential equation is an equation where the unknown, or the variable, represents a function. And the equation has the function and maybe some of its derivatives in it. That's called a differential equation. And we've seen one or two of these before. So we have a theorem in section 3.8, theorem 2, which says the only solutions to this type of differential equation where dy dt equals ky, the only solutions are exponential functions of the form y of t equals some constant c times e to the kt, where k is the same k that was in the differential equation. And c is always the initial value of the function. So y of 0 is just the value of the function at time t equals 0. We call that the initial value. So different types of functions satisfy that differential equation and turn out to be exponential functions. So if they're increasing functions, they're said to be growth functions. And k has to be a positive number for that to be, for e to the kt to be an increasing function. If it's a decreasing function, then k will be negative. Okay. Now, what types of functions are exponential growth functions? Well, we just saw one, population. Compound interest is an exponential growth function. Infection rates, like the COVID-19 infection rate, that's an exponential growth function. An example of a decay function would be the radioactive decay of carbon-14, and that's used for carbon dating in archaeology to find out or figure out how old a fossil is, or in forensic science, we're trying to figure out when somebody died. So those are decay functions. Also, temperature. When something is cooling, that's an exponential decay function, but also when something is warming, that could be an exponential growth function. And so our function, p of t equals 500 times 2 to the t, doesn't quite look like y of 0 times e to the kt, right? Our base is 2. And I just told you that these functions all have the form y of 0 times e to the kt. So where's the e, right? So we can rewrite our function p of t. Remember, the number 2 can be written as e to the natural log of 2. So it's really 2 to the t is really e to the natural log of 2 raised to the t. And now we're using the properties of exponents. When you take e, raise it to a power, and then raise that to another power, you can just multiply the exponents. So we really have 500 times e to the natural log of 2 times t. And notice that does have the form e to the kt. And k is just natural log of 2, which I actually told you a few minutes ago. So our function, our bacteria culture function, is a natural exponential function. We just wrote it in base 2 instead of base e. All right, so we'll see more examples in more videos, and I'll see you there.